The Earth is a weird place. It's a wonderful place. And although it may just seem like a blue marble in space, there are several, and I mean loads, of underlying systems and underlying equations that determine everything that happens here. I am so eager for you to join me as I take a deeper dive into the inner workings of chaos theory and the butterfly effect to see how they affect us, why it's so important in predicting the future, and how we can really harness its power to make our simulations, calculations, and predictions as accurate as possible. This has a lot of impacts on everything that we do in life, and I really hope that you enjoy it, take it on board, and apply it in your own life and think about it critically. This is a mind-boggling episode. You might need to listen to it a few times to really get to grips with what I'm saying, but I hope you enjoy it. It's a great one, this one. As always, I'm Aryan Shah, and I'm your host right here on TES, the EarthSci show. You see, normal science can extrapolate things like gravity, chemical concentrations, but what I'm actually talking about here definitely does not fit this dogma, because a system can be described as deterministic if we can predict exactly what it's going to do, when and how, using the laws of physics. Like if you wanted to predict the speed of a bowling ball falling from a height, well, we know its weight, we know its mass, we know the height, as I just said. That's easy stuff, really easy. But where it starts to get difficult is where you try and predict the weather more than 7 days in advance. Life in general, our planet, everything we know is part of a massive complex system, and within those are smaller complex systems. And in my opinion, the only way we can understand them is by simulating, making realistic models, and by predicting events that actually can occur in the future. And as I said, it's like making weather forecasts. That's the best example, really. Understanding the orbit of planets, calculating the path of hurricanes, tornadoes, natural disasters. And all of these different complex systems appear to follow random patterns at times. But the thing is, it's not random at all, because no day will have the same weather forecast as another day. You won't find the same weather on 2 days in a year, or at all. There will always be some discrepancy. No tornado will follow the same path as another tornado. No hurricane will follow the same path as another hurricane. And so this is because underlying these systems are their sensitivity to initial conditions and parameters. So what that means is that they are so sensitive to everything that you put in to calculate their path. So even if there's a small mistake, a small discrepancy, a small error in how you calculate the path of a hurricane, then you'll get a completely different result to what you expected. But the thing is, as much as we predict, as much as we simulate, as much as we model, even with the most powerful supercomputers in the world, there will always be some rounding error, some significant figure error present. We will never get the perfect answer, the perfect calculation. There's always going to be some extent of degree of accuracy to which we can attain, but we won't actually get it, because nothing that we calculate is ever perfect. It's just the way nature is, really, and we can't predict nature's course in its entirety. And that is what I mean when I say non-linear. It means it's not straightforward, it's not easy to calculate, and it doesn't follow the linear projection that you can expect. Calculating the speed of a bowling ball, that is linear, because there are very few inputs into that equation to find out the speed. Whereas something like a hurricane, there is so much that goes into calculating, so many errors that can be made. It's not straightforward at all. And this is the exact basis of chaos theory. Or you may have heard of it as the butterfly effect. Now, the first place and the best place where I heard about chaos theory was the movie Jurassic Park, where good old Jeff Goldblum played Ian Malcolm, the mathematician, the chaos theorist in the movies. Now, I didn't know what he was talking about. I had no clue. I read the book, I still had no clue until I watched one video on YouTube and I did my own reading on chaos theory, and now it still doesn't make sense. Okay, no, I'm joking. It actually does to a certain extent, but hopefully I can help you understand what it is, why it's so weird, and how it can actually help in life. Now, one way you can actually think about chaos theory is thinking about the butterfly effect. So this is where Travis Scott jumps on stage. Oh, no, sorry, that's the wrong butterfly effect. I meant to say that the idea is a butterfly flaps its wings in South America and causes a hurricane in Asia. Is that even possible? Well, theoretically, yes, because if the butterfly hadn't flapped its wings at exactly the right time in the right place, then a hurricane wouldn't have happened in Asia. And this is just crazy because it contains a lot of nonlinear equations. There's a lot that goes into this. Wind speed, wind movement, temperature, and humidity, for example. But you can see what I mean when you can't really predict this stuff, right? There's no way for you to predict when the butterfly will flap its wings, where, and how. And it's not even just the butterfly, it's a load of different factors that lead up to the hurricane happening later on in the future. It's one small thing happening in the input that leads to a much larger event in the output. So keep that in your head for a sec. And there are, of course, models of the weather that help us predict natural disasters, when it's going to rain and so on. But there's no way for us to actually make a perfectly accurate model because there are so many factors that need to be considered, that need to have been accounted for. And for example, if you want to calculate when it's going to rain, you need to measure like every square centimeter of atmosphere in the area that you want to make it accurate. But obviously, we're not going to do that. And so our calculation won't be as accurate as we want it to be. And even if you have an equation for the weather, it's going to be nonlinear, as I just said. It's going to be really complex because it has a lot of factors involved. And there's going to be an almost infinite number of input values needed to calculate the weather. But even if we had the tiniest calculation error or the smallest inaccuracy possible, this would lead to huge fluctuations in our result. According to Wally Smith Brucker in his book, How to Build a Habitable Planet, I definitely recommend that actually. It's really good. I'm reading it for university and it's helped quite a lot. So his quote was, "Chaos occurs in common equations where the outcome is so sensitive to the tiniest of changes in the initial conditions or constants in the equations that long-term prediction is impossible." So what he's trying to say is that the nature of chaos theory just makes it so hard for you to predict behavior of a complex system later on in time. And just because the results could fluctuate at the tiniest error or at a change in equilibrium. So yet again, a small change in the input, a small mistake in the parameters with which you're calculating leads to a mess up at the end, massive fluctuations because the equations are so complex, the system is so complex and it involves so many things that if you mess up even the tiniest bit, that's it, you're screwed, you're finished. But the good thing about this that I like thinking about is equilibrium. That's a good word. So if the conditions are perfect, then the output would probably be perfect as well. But as I said, we have small inaccuracies and differences in the input that steers the output away from the equilibrated value. So if you think about a sine curve, the middle line is the equilibrium, and the waves, they're moving away from that equilibrated state all the time, as you can see here on the diagram. But that's the thing. You need to read the article that I'm going to be writing alongside this a few times maybe. You need to listen to this episode a few times to properly understand what I'm saying here. Trust me, I had to do the exact same thing, so we're in this boat together. And I know that I keep talking about factors, I keep talking about the input, the output, all of the discrepancies, these small changes in the initial conditions. I know I keep talking about them, but trust me, the more I hammer it home, the more you understand exactly how important these small key words are to understanding the basis of chaos theory. But if you want to take a deeper dive into chaos theory, and there's a few different ways of thinking about chaos theory. Number one, you have mixing. So 2 points in a system, like 2 water molecules in the ocean, they are together at first and then they end up far away from each other after an amount of time. After they've interacted once, they'll never do it ever again because of all the different factors that cause them to become separated in that system and the far varying initial conditions involved. Number two, we've got unpredictability. So the idea that complex systems like atmospheres and ocean systems, plate tectonics, they follow a non-linear equation, and any change in the initial parameters leads to a distinct and drastic change in the output. Now that's a great quote from the Fractal Foundation website and explains it quite nicely. And number three, have feedback. So things like the stock market, the value of stock rises and falls throughout the year based on different events. Then people buy or sell their stock according to that, relative to the prices of the stock. And that affects the stock prices again, the value of them. It changes because people buy and sell. And so that's an endless cycle. That's a feedback loop. So as I said, check out their website. It's pretty good. But one thing I want to say is, as an earth scientist, I want to see how relevant chaos theory really is to my field. So again, in How to Build a Habitable Planet, Brooker says, understanding of the systems on our planet requires knowledge of the individual parts. So the energy that drives a system, the cycles, the feedback loops that are there. So we need to understand the large and small scales involved in all of these different systems. And then we can understand the evolution and the story of planet Earth. And so, in my eyes, chaos theory is basically everywhere. Literally everywhere. Because no system on Earth is simple. I find that impossible. Okay? It's virtually impossible for us to accurately simulate and predict events on our planet because there are so many complex systems, because chaos theory is everywhere. And remember, with chaos theory, you cannot accurately, to the highest degree of accuracy, predict anything. Even though technology has come so far, even though we're a really smart species, or we like to think we are, we still can't predict fully what will happen. Okay? And now, as Broca said, we need an in-depth knowledge of how many components are in our systems, and we got to understand them. So as I said, the oceans, the atmosphere, plate tectonics. But what if we can manipulate chaos theory to our own will? What if, instead of seeing chaos theory as the enemy, as an obstacle in our path, we actually use it to our advantage? We use chaos theory to refine and to fine-tune our calculations, simulations, and models to make our predictions as accurate as possible. This means taking into account the different ways we can think about chaos theory, such as unpredictability and mixing, that two things will not interact with each other ever again after they have the first time. If we include that in our calculations and in our simulations, I guarantee you that they will be the best that they have ever been. By taking into account things that we are not prepared for, we actually become more prepared. A great example is satellites collecting data for weather forecasts. Before, they just collected one bit of data and that's it, and they measured one area. But no, now satellites are measuring more areas than ever and reduce the room for error. Basically, they reduce the extent to which there are discrepancies in the measurement. Just think how much we could get done if we make higher accuracy models using chaos theory to its full extent. We could literally avoid natural disasters killing so many people. We could save millions of lives every year. We could explore new depths of our oceans by understanding patterns of the general circulation model, the thermohaline circulation, which is about temperature and salt concentrations. Because imagine if we can model those circulations and the concentrations to a higher degree with chaos theory in mind, taking that into account, which we previously hadn't, then we can explore more and we can actually dive down and venture to these final frontiers of exploration. And talking about final frontiers, do check out episode 3 with Dr. Yi Chao from C-Trek, previously worked at NASA's Jet Propulsion Lab. He's doing some great work with his company C-Trek on ocean floor mapping, and the tech that they use is fantastic. I was actually blown away by that. So do check it out. It's a great episode. And we can't perfectly predict in the earth sciences using chaos theory, but we can predict better. Okay, so listen to that again. We can't predict perfectly in the earth sciences using chaos theory, but we can predict better with chaos theory at our side and in our minds at all times. I think this is an untapped resource, if you ask me. It's an untapped resource. It's literally like going into the oceans with twice the size of Mars being unmapped, an area twice the size of Mars being unmapped. We don't know anything about our oceans, in my opinion. Similarly, we don't know anything about modeling, simulations, and mapping of anything on our planet, complex systems. Same way. So we really need to harness the power of chaos theory and let it make our models, simulations, and understanding of the world we live in as representative and as fine-tuned as possible. And you know what? When I started this episode, I didn't think I'd be talking so much about it, but it actually makes a lot of sense because we haven't we have a resource that we're not using and we can use. So many people don't know about chaos theory, the beauty of it, why it's so strange, and how we can use it to the best of its abilities. But that's my job on this podcast, to make you more aware about random things, strange things, beautiful things in the earth sciences and general life that we can use to take our species from here to up there. All right? So then again, you might be thinking about, how does chaos theory, what this dude is talking about, how does that compare to anything else that we see in nature? And so one key thing that I'd like for you to do is to compare stochastics to chaos theory. And let me explain that right now. If you think about it, whilst chaotic systems appear predictable in the short term, in the long term, they become hard to foresee, hard to forecast, and just appear to be random. But as we all know, as I've discussed with you guys, there are these underlying conditions and sensitivity to initial parameters and conditions involved as well. But then we compare that to stochastic motion, and that is just entirely random phenomena happening in nature. And an example is Brownian motion, when thinking about how smoke particles move throughout the air, throughout the atmosphere. There's no way we can predict that. It is completely random. So once again, chaotic systems are predictable. They're deterministic to a small extent and then become unforeseeable, whereas stochastics, they are completely unpredictable. They are completely random. I thoroughly recommend you do your own reading, your own research on stochastics and Brownian motion, because it's actually used in the finance world, in the stock market, in robotics, in geology, in celestial dynamics, which is to do with space and how rocks and bodies move through space. All these different disciplines and subjects have elements that rely on Brownian motion and stochastics. And I don't have enough time to go into the nitty-gritty details of it, but this is just a short summary about it and why it's important to compare it to chaos theory. But once again, I think it's really interesting and it's a topic for another day. At the end of the day, I think it's really important for you to compare what I'm talking about today, chaos theory, the butterfly effect, all of that. It's important for you to compare that to everything else that we see around us, so you get a relative idea of how important it is and how it can help us in life. So you can really see from this comparison that chaos theory, it does help us predict the future. It does, to a certain extent. And that's why I think it's important. Whilst it does have its many limitations, as I described previously in this episode, I think it's still really beneficial. It's an untapped resource, and we ought to think more about it when making our models, simulations, and calculations about what's going to happen later on. Whether it's going to save lives by helping us to predict and prevent the large-scale impacts of natural disasters, or really just help us understand the world that we live in, this wonderful, complex, large-scale and smaller-scale systems that we're all involved in, and how we can just appreciate it more. Because really, on this show, I want you to appreciate our planet, where we come from, and why it's so important to us all. And I think chaos theory, it's weird, it's wonderful, and it's a great way to understand the maths, the biology, the physics, the entire conglomerate of different subjects and disciplines needed to understand the world that we live in, and how it facilitates life as we know it, all of its complex systems, in such a graceful way. So I've talked about why chaos theory is so good, but I think it's equally important to talk about its limitations in life and how it works. So one reason why people shun away from chaos theory is because it's quite similar to statistics in the way it works, in the fact that you can't really predict a certain behavior from a single stat, a single statistic, but you can tell how it should behave within a certain range. So I'll say that again, you can't really predict exactly how something will act, but you can get a general idea of how it may act in the future. For example, if we're predicting where an asteroid is going to pass through on its way to Earth to kill us all, it might not pass through this exact coordinate in time and space, but it may fall within this range, within this distance in space. And so we get a general idea of what's going on with this asteroid and where it's headed. It's not exact, but it's about right. And you know what? This is probably going to upset a lot of people who need the exact statistic, the exact data for their calculations, because some people don't need ranges. They need the precise locations, the precise coordinates, for example, for whatever they're working on. And so chaos theory won't actually work or cooperate with what they're doing. Continuing on from that, I think that time is a massive limitation when it comes to thinking about chaos theory and its applications to whatever industry you're working in. Because whilst there is randomness, whilst there are these bizarre patterns that may occur in nature everywhere that we look, as time goes on, the number of factors affecting and influencing what can happen in a complex system increases. And so our ability to predict something happening in the future becomes severely and significantly reduced. So that means that whatever degree of accuracy you have, even if you have no rounding errors, there is still going to be a massive problem with chaos theory just because of the nature of time. Well, I hope you enjoyed this episode. It was a quick one, but a really nice one, I thought, because chaos theory, it's something I haven't really thought about before until I watched Jurassic Park again for the 15,000th time. And I thought, okay, I can give this to my listeners. I can use it in the earth sciences for something good. I could teach people about it. I could teach myself about maths, about complex maths, nonlinear dynamics, that kind of jazz. So I hope you enjoyed it. I know I did. Feel free to leave a comment or email me at sciencethatstuff@gmail.com. And so that concludes this episode. I hope you understood chaos theory. So basically, just a quick summary, it is the smallest input value, the smallest mistake or inaccuracy in the input value could lead to a disastrous, massive fluctuation in the output value because the system is so complex and there are so many factors involved. But don't forget that it can help us to predict the future and the behavior of really weird systems in the short term, and it has unforeseeable consequences in the long term. Join me next time as we continue our journey to explore the most pressing questions and issues of our very own planet Earth. Don't forget to subscribe and leave a review on any streaming platform. I'm Aryan Shah, and you're listening to The EarthSci Show.